Hello students, happy morning. Class 12 Physics, Unit 7, Wave Optics continuation video. In our previous class, we discussed the important phenomena of light that shows a wave nature, that is interference. We know interference is a phenomenon of superposition of two waves. By interference, it may be a constructive interference or destructive interference. If constructive interference takes place at a point, the point will be bright. If destructive interference takes place at a point, then the point will be dark. This constructive and destructive interference that depends only on the path difference between the wave, and we also studied about the interference fringes, that means interference pattern in Young double slit experiment. By this experiment we get the equation for path difference and also we get the equation for bandwidth. Okay, from the help of the interference pattern we know that we get a central bright band, okay, and followed by that we get a alternate dark and bright bands with equal spacing in order of using a monochromatic light. If we use a polychromatic light, that means white light, we get a colored fringes with a varied thickness. Here from today onwards, let's start our new phenomena of light that shows a wave nature, that is diffraction. Diffraction, that means bending of waves. Okay, diffraction means bending of waves. Here diffraction is a common characteristics for both sound wave and light wave. Sound wave and light wave. First, let us start our discussion from sound wave. If you are in a house, that house consists of several rooms. Okay, here there is a room. In that room, there will be a speaker. That speaker playing a song. Okay, here one more room. That is here. Inside that a person is sitting. He can listen the song. Okay, because of diffraction phenomenon. See, the sound from the speaker can travel through this part. Okay, because of diffraction. Diffraction means bending of the waves. Okay, see, this is the obstacle. That obstacle size is considered as A. If the obstacle size is comparable to the wavelength of the wave, then diffraction is possible. Okay, diffraction means bending of waves. For this case also diffraction possible. A is greater than lambda. It is little greater than lambda, equal to or greater than lambda. For this case diffraction is possible. Because of this we can hear the sound wave from a long distance. Okay, then let me explain it for light waves. Light as a wave. Okay, light wave. We know, if suppose in a dark room I switch on a torch. Here there is a wall. In that wall we can get the light like this. We get a central spot will be having the maximum intensity, and the next distance increases, then intensity decreases. Okay, here it is a violation to the rectilinear propagation of light. Okay, we studied in ray optics light travel in a straight line, but here I am telling light is spreading in a geometrically shadowed region. Okay, in ray optics we know light always travel in a straight line. In this path it have to travel. But if we switch on a torch in a dark room, then it will spread in a geometrically shadowed region. This is a geometrical shadow region according to ray optics. Okay, this shows here intensity will be maximum, then goes on it will decrease. Okay, this is the first minima. Okay, then after that we get a maxima. Okay, this is the first minimum. After that we get a maximum. I can indicate here. See, it is a center point O. Okay, we get a pattern like this. This is the first minimum. Here this is the first minimum. In between the first two minimas we get a central maximum. Central maxima. Okay, we know for the possibility of diffraction we need the obstacles having the size that is comparable to the wavelength of the light, or that is little much greater than the wavelength. Okay, for this condition obeyed, then the diffraction will be possible. Here the two scientists, Fresnel and Fraunhofer, in order to explain the diffraction phenomena, he conducted two experiments. Okay, first one, let we see for the Fresnel's diffraction. For that he considered a single slit. Okay, here it is a slit. The size of that slit will be A. Okay, that size will be comparable to the wavelength of light used. Here I use a point source. Okay, we know from that point source the wave font will be a spherical wave font. Okay, here there will be a screen that is far away from the slit. Here it is screen. From that we observe that there will be two light waves from the slit. It overlap at a point P. Okay, here also it overlap at a point P dash. This region will be bright. We then followed by that we get a dark fringes. That means dark region. Okay, that is minima. This is Fresnel diffraction. For that he used a single slit and then use a point source. Okay, this produces a spherical wavefront. We can also use a line source. That thing we know that can produce a cylindrical wavefront. Okay, then it is difficult because we get the image in a long distance. It is not get in a lab. Okay, because the screen and slit are at a long distance. Okay, then in order to rectify this, Fraunhofer did an experiment. Here in Fraunhofer diffraction he also considered a single slit experiment. Okay, the size of the slit is comparable to the wavelength of the light used. Here he also using a point source, but he need a plane wavefront. Okay, we know the wavefront coming from a point source will be a spherical wavefront. In order to get a plane wavefront, here he is placing a converging lens. We know the converging lens make this ray that is parallel. Okay, here this is a plane wavefront. In order to combine this wave, here I am placing a one more converging lens. Okay, then I am placing a screen that is at the focus of the lens 2. Here lens 2, it is a lens 1. We know the parallel rays coming towards the lens, after emerging it will meet at a point that is the focus of the lens. Okay, here we get a bright band or bright fringes. Okay, here we know according to Huygens principle all the point on a wave font, okay, that behave as a source for secondary wavelet. Here this is a wave font, then I consider a wavelet like this, then it will meet at a point P. Okay, that also we can draw in this way also. Then we get a pattern like this. Okay, see, here it is easy to observe and analysis because it need small distance. Okay, first of all, here we are using a plane wavefront. In Fresnel's we are using a spherical or cylindrical wavefront. Here light source is from finite distance in Fresnel's. Okay, here plane wavefront is coming from infinite distance. Okay, then in Fresnel's we are not using the convex lens. Okay, but here we are using a convex lens. Fresnel's, that is difficult to analysis. Here it is Fraunhofer, it is easy to analysis and observe. Okay, let me see single slit diffraction. Okay, we are explaining the Fresnel's diffraction, that is known as diffraction in single slit. Diffraction in single slit. It is nothing but the Fraunhofer diffraction. Okay, for that we know we need to consider a slit having the size A that is comparable to the wavelength of the light used. Here I am using a point source, then the point source produce a spherical wavefront. Here at that point I placed lens 1, that is a converging lens, we get a plane wavefront. Okay, at this path there will be a one more lens, that is lens 2. Here also it is a converging lens. The focus of the lens, at the focus of lens I placed a screen. It is at a distance d from the slit. Okay, here we know the lens will converge the parallel rays at the focus. Okay, the point will be said to be O, it will be bright. Okay, because there is no path difference. Then here we know according to Eigen principle, all the point on the wavefront that behave as a source for secondary wavelet. Here I consider a wavefront, then I draw a waves at an angle theta with the perpendicular line that drawn with the screen. Okay, then here these parallel rays converge at the point P on the screen. Okay, up to which the central maxima spread. Okay, up to which the central maxima spread. Okay, then at that point we get a first minima. This one will be a first minima, this one will be a first maxima. Here also we get a first maxima. Okay, in between the first two minima, here also first minima, there will be a central maxima. Okay, here our aim is to find the path difference between these waves. Okay, and also we know the dark and bright fringes. Okay, the dark spot and the white spot, that depends only on the path difference. Okay, if suppose the point P, that will be a minima, that means dark, then let me see what is the condition P to be minima. Let me see the condition for P to be various minima. It may be first minima, second minima or nth minima. Okay, in order to describe the point P to be minima, we have to split the width of the slit in even numbers. Okay, condition for point P to be various minima, that means destructive interference. Okay, various minima. Destructive interference. See, first of all we have to divide the width of the slit that is a in even number. Even number. Okay, first let me see for the condition for p to be first minima. Okay, this is the first minima, this one and this one will be a first minima. In between the first minimas there will be a central maxima. Okay, condition for p to be first minima. Okay, in order to find the first minima at the point P, we have to separate or divide the width A as even number. Here I am dividing it as half. Okay, A by 2. A became A by 2. That means here this is a slit size, that is A. Here the width of the slit, here I am dividing it as A by 2. Then A by 2. Okay, this is a screen, this is a lens. Okay, okay, see this point and this point having the distance a by 2, so these 2 points are corresponding points. Okay, and this point will be a corresponding point because the distance is a by 2. This point and this point that are separated by the same distance a by 2, so it is said to be a corresponding point. Here I consider here 2 light waves from that corresponding point that intersect at a point P, that having the phase difference, that is pi. We know phase difference is pi, then the path difference will be delta is equal to lambda by 2. Okay, here this is, we know theta, here this is delta, that is a path difference. We can find the path difference, so we can write sin theta is equal to opposite side delta by adjacent side, that is a by 2. Okay, then we can write delta as delta is equal to a by 2 sin theta. We can equate delta as lambda by 2, then we get a by 2 sin theta is equal to lambda by 2, then 2 cancel, then a sin theta is equal to lambda. This is an important expression for the point P to be first minima. Okay, this is a condition for point P to be first minima. Here theta is the angular spread of maxima. Okay, up to which the central maxima that spreads. Okay, condition for P to be first minima. Then condition for P to be second minimum. Okay, for that we have to split the width A as A by 4. For first minima that is A by 2, for second minima that is A by 4. Then we know A by 4 sin theta is equal to, here it is again lambda by 2. Okay, after solving this, then we get A sin theta is equal to 2 lambda. Okay, then for the condition for P to be third minimum, for that we have to split the width of the slit as A by 6. Okay, then we get A by 6 sin theta is equal to lambda by 2. After solving this, we get A sin theta is equal to 3 lambda. Okay, in general we can write the condition for minima, that is the condition for that means nth minima. Okay, condition for nth minima, condition for nth minima, that is A sin theta is equal to 2n, we have to split A as 2n. Okay, that means A is splitted as A by 2n. Okay, then a by 2n sin theta is equal to lambda by 2. 2 going to cancel, then we get a sin theta is equal to n lambda. Okay, here it is a general equation for the condition for nth nth minima. Okay, here n is the order of diffraction. Order of diffraction minima. Okay, here in this case we are splitting the with the a as even numbers. Okay, splitting it as a by 2 and a by 4 and then a by 6 and a by 2n. Okay, here the each wave from the corresponding point then cancel with one another. Okay, so the point P will be dark. That means constructive interference take place. Okay, light produced from the corresponding points are cancelled with one another. Light produced from corresponding points are cancelled with one another. Okay, then let me see for the maxima. That means then condition for maxima. That means the point P will be bright. Okay, for this case we have to split the width of the slit as odd number. Okay, let me see first one, that is for first maxima. For first maxima, the slit width is divided as a by 3. Okay, that means a is splitted as 3 equal parts. Okay, see here, this is the slit. The overall distance is a. The distance a is split as a by 3, a by 3, a by 3. Okay, this one a by 3, this one a by 3, this one a by 3. Okay, and each point in the slit at a distance of a by 3 is said to be a corresponding point. Here there is a lens, this is a screen. The light from that wave that overlap at a point P, here constructive interference take place, so the point P will be bright. Okay, here let me see for the first maxima. We know a by 3 sin theta is equal to the path difference, that is lambda by 2. Okay, then after solving we get a sin theta is equal to 3 by 2 lambda. This is a condition for point P to be first maxima. Then for second maxima, we are splitting a as a by 5. That means a is splitted as 5 equal parts. Okay, then we get a by 5 sin theta is equal to lambda by 2. After solving this we get a sin theta is equal to 5 by 2 lambda. Okay, then condition for nth maxima. Therefore I am dividing a as a by 2n plus 1. Okay, a as a by 2n plus 1. We can write a by 2n plus 1 sin theta is equal to lambda by 2. After solving we get a sin theta is equal to 2n plus 1 lambda by 2. Okay, here n is the order of diffraction for destructive interference, sorry, constructive interference, that means maxima. Here n is equal to 0, 1, 2. For that case, that is start from 1. Here for the odd equal parts, one part will be remain uncancelled by another parts. It make the point P bright. For that minima, even numbers, one part will be cancelled by other part. Here for odd numbers, for if suppose there is a three parts, first and second part are cancelled with one another, then third part will be uncancelled by anyone. Okay, so the point P will be bright. Our next topic, that is discussion for first minima. Actually the topic is discussion of first minima for the central maxima. Okay, we know we get the pattern like this, diffraction pattern like this. Okay, here it is a zeroth maxima or central maxima. This one is a first minima. This also a first minima. Okay, in between the two first minima, we get the central maxima. Okay, we know the equation for the first minima, that is equation for first minima. First minima is a sin theta is equal to lambda. Okay, this is a condition for first minima. In between these two minima, we get a central maxima. Here we know theta is a angular spread of first minima. Spread for first minima, up to which the first minima spread. Okay, we can write this one as sin theta is equal to lambda by a. Here we know the central maxima is intermediate between the first two minima, that means first minima. Okay, here let me see the case for the central maxima. Case for central maxima. We know sin theta is equal to lambda by a. In first case, if the size of the slit, that is less than lambda, for this case we get sin theta value will be less than 1. Okay, sorry, sin theta value will be greater than 1. There is we know the maximum value of sin is 1. Maximum value of sin is 1. So here we are getting sin theta that is greater than 1. It is not possible. So diffraction not possible. Okay, it is not possible. So no diffraction. Okay, in second case I consider if the size of the slit is equal to lambda. For this case we get sin theta is equal to lambda by lambda, we get 1. Sin theta is equal to 1. Okay, it means we get the diffraction. Okay, so the first minima that at an angle of in which degree sin theta will be 1, that is 90 degree. The diffraction of first minima take place at 90 degree. Okay, that means the central maxima spread fully into the geometrically shadowed region. Okay, we get 90 degree. Okay, theta is equal to 90 degree. That means we get entire part will be bright. Okay, this is possible for the width of the slit is equal to the wavelength of the light used. Okay, then third case, that is if a is greater than lambda or comparable to lambda. Comparable to lambda. If suppose I consider a is equal to 2 lambda. Okay, for this case we can write sin theta is equal to lambda by 2 lambda, that became 1 by 2. We know sin which degree is 1 by 2? Theta is equal to 30 degree. Okay, here diffraction take place. For this case diffraction will be take place. Take place at an angle. Take place at an angle 30 degree. Okay, then last case, that is size of the slit is greater than lambda. For this case we get sin theta is less than 1. Okay, that means we get a first minima. Okay, in a we get a first minima within the width of the slit. Okay, here this is a opening, here this is a width of the slit. We get the first minima in this region alone. Okay, the point P will be dark. For this case A is greater than lambda. The first minima is in a ray optics region. Then we are concluding that the width of the slit A must be few times greater than, that means few times greater than the lambda. Okay, if it is possible, then the diffraction also will be possible. Okay, then our next topic, that is Fresnel's distance. Fresnel's distance. We know in ray optics light travel in a straight line, but here we are telling light will bend, that is known as diffraction. Okay, Fresnel did an experiment. We know he is using a single slit, then there is a point source, there will be a screen at a longer distance. Okay, here the light from the source, it have to travel in a straight line, that obey ray optics. Okay, we know from our 6th lesson, we know light always travel in a straight line like this. Okay, but in wave optics, according to diffraction phenomena, the light will bend its path. Okay, here it is a center point, light wave will bend. Okay, see, up to which the ray optics obeyed. Okay, beyond that the wave optics will be significant. That distance is known as Fresnel distance. Here it is a width of the slit. Okay, here I drawn a line, this is theta, so we can write this is a by 2. Okay, see, the ray of light always travel in a straight line from our ray optics. Here up to this distance ray optics obeyed, beyond that wave optics obeyed. Okay, see, up to the distance is set, the ray optics obeyed, beyond that wave optics will be significant. That distance is known as Fresnel distance. Okay, here let me find the value of Z, that is Fresnel distance. If suppose we know the diffraction equation in first minima, equation for first minima, that is A sin theta is equal to lambda. Okay, after solving this we get sin theta is equal to lambda by A. Here we know the value of theta is very small, that is small. We can take sin theta is equal to tan theta, that is equal to theta. Okay, then theta is equal to lambda by A. Then we can say this one is tan theta, then tan theta is equal to opposite side by adjacent side. Okay, tan theta is equal to opposite side is A by 2, adjacent side is Z. Okay, we know tan theta is equal to theta, that the value will be equal to sin theta. Then we can write theta is equal to A by 2Z. This one is equation 1, this one is equation 2, equating 1 and 2. Then we get A by 2Z, that is equal to lambda by A. Then solving we get the value of Z, that Z is equal to A square by 2 lambda. This Z is nothing but a Fresnel distance. Okay, Fresnel distance is a distance up to which the ray optics obeyed. Beyond that the wave optics became significant. Okay, students, in today's class we discussed about the diffraction phenomena. Diffraction means bending of waves. Okay, because of diffraction we can feel the sound from anywhere. Okay, for diffraction possible, the opening of the slit must be comparable to the wavelength of the wave. For light wave, that is comparable, that means equal to the wavelength, or that must be greater than wavelength, little greater than wavelength. Then only diffraction will be possible. We get a diffraction pattern. In interference we get a interference pattern. These two patterns will be comparable. In interference pattern, the interference fringes having the equally spaced. Okay, in diffraction pattern we get a central maxima, then after that we get a equally spaced minimas. Okay,